Hey everyone, welcome back. So today I would like to talk about intermolecular forces, and I want to close this topic before we actually proceed to biochemistry and molecular biology. Finally. So intermolecular forces are basically the forces between different molecules in space, in our system. And we saw my example that I gave a few lessons ago was intermolecular forces between water molecules. And because we have oxygen or nitrogen or fluoride connected to hydrogen, we have hydrogen force, hydrogen bonds between different molecules. So when it comes to water, we have H2O. If we had one of the following elements, we said that we have hydrogen bonds. So H2O creates and makes hydrogen bonds within different water molecules, different polar water molecules. It's a very strong intermolecular force, but we have something even stronger. I also talked about something called the Ionic Compound. So molecules are when you share electrons within the cloud, within the different electrons, and you have the share of electrons to complete different octet and different electron levels. And this happens when you have under 1.9 difference in electronegativity. But when the difference in electronegativity is really high, you have something called ionic compound. Basically, the most basic example that they usually give in textbooks is table salt, which is NaCl. So NaCl is made out of sodium and chloride. So it's basically sodium chloride. And the difference in electronegativity is very big. Chloride is around 3.5, while sodium is only 0.9, which is, let's say it's 1. The difference is way bigger than 1.9. So what do we have for when we have the way bigger than 1.9? We have the chloride, the very electronegative element, just stealing the electron from the sodium. And when it steals the electron from the sodium, you don't have a molecule. You basically have something called a lattice. So if you see salt, it's solid in room temperature, and the state where it founds is basically many chloride and sodium atoms found together in a very organized way in an infinite block of structure. So you can have billions and billions and billions of atoms just in the following way, organized in the following way, and it can be infinite in size, depends on different things of course, but just infinite in size. So you have chlorides and chloride and sodium all together stealing electrons from each other. And this interaction, this intermolecular force is the strongest intermolecular force we have in nature. What does it mean when we have such a strong intermolecular forces? It means that in order to melt or to boil salt, which has ion-ion interaction because you have sodium and chloride interactions, it means that you need to spend a lot of energy to break the following bonds, because the big difference in electronegativity causes them to be attracted together so much. So this is our strongest intermolecular force. The next one would be ion dipole. Before I proceed, I'm going to explain what dipole is. So dipole, do you remember that I told you about the molecule of water itself? And because oxygen is 3.5 and hydrogen is 2.2, you have a very big difference in electronegativity. And when you have a very big difference in electronegativity, you have the dipole in the molecule. You have two poles in the molecule. One of them is minus and the other one is plus. So this is when it comes actually and when we see it. So this is called dipole inside the molecule. The ion would be the interaction with an ionic compound. So for example, the most basic example is to take a glass of water and to take a spoon with some salt and to put the salt inside. The salt will dissolve because of the ion dipole interactions. The dipole, the polarity of the water, will interact with the negative charge and the positive charge ions, and it will cause them to lose their very order orientation in space. So if we will take the molecule, the water, and we have oxygen and hydrogen, the hydrogen, which is the more positive part, will interact with chloride, which is the negative part, the negative ion, and the oxygen, which is the negative charge, has a negative charge, will interact with the sodium with a positive charge. And this is called ion-dipole interaction. And it's very important to remember. When you have the ionic compound that is polar inside a polar solvent, this is the ion-dipole interaction. The next one is dipole-dipole. So when you have many, for example, water molecules that are being attracted and interact with each other through the hydrogen bonds, this is where we say it's called dipole-dipole interaction, because you have dipole here, and 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 all the plus and minuses are constantly being attracted and charged together. And because we have a permanent dipole inside the molecule, we always have very strong interaction between the molecules. But what happens when we don't have a polar molecule? Do we still have any interaction between the atoms, between the molecules? So yes, we do. This is called van der Waals interaction. Van der Waals, okay, let me go back a bit. Dipole-dipole can only occur between polar covalent bonds, between polar covalent compounds, between molecules that have permanent charge. Ion-ion interaction can only occur between ions. Ion-dipole can only occur between polar molecules and ions. But van der Waals basically can occur between anything. Why? What is van der Waals? Let me explain in a few seconds. So let me delete. Okay. So van der Waals is pretty straightforward. We said electrons are statistically likely to be in different places around the molecule. When it comes to dipole, the electrons are statistically more likely to be on one side of the molecule compared to the other side of the molecule. But when it comes to regular molecules, we also have the random spread, the random cloud of electrons as well. And from time to time, we have something called momentary dipole. What does it mean to have a momentary dipole? It means that we have the cloud of electrons in a split of a seconds, sometimes around time, the electrons will go to one side more than the other. It will suddenly cause a very temporary dipole inside the molecule. And the very temporary, the split of a second where the electrons are more likely to be in one side compared to another, will affect all of the molecules around it. So while we have permanent dipole when it comes to polar molecules, we have momentary, we have temporary dipole when it comes to molecules that are not polar, because the electrons are so fast and they just all over the place, almost completely random around time. When we have the momentary time in space, when we have electrons that are concentrated more on one side compared to the other side, we will have temporary dipole. And when we have temporary dipole, we will also have the induced dipole between the different molecules. So even though the molecule is not polar and the polarity, the intermolecular forces are less than 0.4 by the scale of electronegativity, and even if it was the same, like zero difference between electronegativity, we do still have induced dipole and momentary dipole and temporary dipole, just because of luck, because of statistics, because the electron can be anywhere around the molecule, and sometimes it happens. The thing is that when it comes to momentary dipole, the bigger the molecule, the higher you are more likely statistically to have induced dipole, temporary dipole. Because when you have a very, very big cloud of electrons and you have more electrons, the more electrons you will have. For example, let's take butane for example. The more electrons you have, the more likely you are to have momentary dipole around the molecule. And the the higher the likelihood to have momentary dipole, the strongest the van der Waals forces are in the molecule. So how does it affect anything that I'm talking about? So it matters because the strongest the intermolecular forces, the more energy you will need to spend in order to break the intermolecular forces, and the higher the molecular point, the boiling point and the melting points will be based on the intermolecular forces. This is why it is so important to remember. So why do we have, for example, water compared to methane? The melting point and the boiling point of methane, it's minus many degrees, comparing to water, which is 100 degrees Celsius, the boiling point. And if you compare it, you would see that the intermolecular forces of water are way stronger than the intermolecular forces of this non-polar compound. Because this one is van der Waals, and this one is dipole-dipole. Now, the order of strength when it comes to intermolecular forces is the weakest is the van der Waals. Then you have the van der Waals molecule, the non-covalent plus covalent. Then you have dipole-dipole. And then you have ion dipole, and then you have ion-ion. The boiling and melting point increased based on the strength of the intermolecular forces. It's very important to remember. And I hope this video made sense, and I hope we close this part of the lessons when I talked about the intermolecular forces. So beyond the hydrogen bonds, you also have many different ways that molecules can interact with each other. And the strongest the intermolecular forces, the higher the boiling and the melting point. I will see you in the next lesson.